So in this video we're going to focus on the idea of the inclined plane, and to simplify things for right now we're going to look at a frictionless inclined plane. So that might be a surface that has no friction, or it could be a car traveling down an inclined plane where there's no friction in the wheels, so that the car can move without any forces that are resisting it. And it's going to lead to kind of an interesting outcome that's going to help us to simplify problems. It's going to really make the problems a lot easier to deal with. And even when we bring friction into it, the problems are still going to be easier to solve using this approach than the old approach, which was to combine kinematic equations with the force equations. So again, that equation v squared equals v naught squared plus 2ad combined with f net equals ma. Those two can be combined to solve every problem that we've looked at in the energy section so far. But the whole idea of the energy approach to it is it's a way that's a much simpler approach, and just conceptually much easier to solve problems. So in order to do this, let's draw an inclined plane. And we'll put a box on the inclined plane. And this box is at some height. And for our purposes, we'll use an angle of 30 degrees. And obviously the box is going to, with no friction, the box will slide down the inclined plane on the basis of there being only two forces acting on the box. One is the normal force, and one is the weight. Okay, and so one thing really important to remember about this is that we change the coordinate system. So when we have an object on an inclined plane like this, we change the coordinate system. We just tilt it like this because it just makes it easier. This makes it easier to work with, because now all of the motion is confined to the x motion, instead of it's going to move both vertically and horizontally, which makes the problem much more complex to deal with. So tilting the coordinate system over on its side like this still gives me two perpendicular coordinates, and what allows me to do then is to kind of focus on the motion only along the plane, right? So in the first example, we're going to use the old way of doing it, and then we'll see that the second way of doing it provides a much easier way of handling it. So the force, the weight would get broken up into two components. This guy would be mg sine theta, and this guy would be mg cosine theta. Okay, and the one that's really important in this case is the mg sine theta, because this is the one that makes it move down the inclined plane. What I know about mg cosine theta and f of n is that the two must be equal, because there's no acceleration along this direction. So perpendicular to the surface, there's nothing happening. It's not moving at all, much less accelerating. So nothing really interesting happening there, but this is the one that's going to provide me with the acceleration. And I want to put some numbers with this thing right now. So we're going to say that this height is equal to, we'll give it 10 meters. Okay, and in that case, if the height is 10 meters on a 30-degree triangle, 30, 60, 90 triangle, then that means that the displacement along here would be 20 meters. Okay, so purposely try to pick easy numbers to work with. So the distance from the inclined plane down to the bottom here is 20 meters, and then the height is 10 meters. Okay? So in the 30, 60, 90 triangle, the short side is half the length of the longest side. Right? That's probably the most significant thing about the 30, 60, 90 triangle. So the box is actually going to travel along this 20-meter path, and here's what I know. I know that the net force acting on the object is ma, and that is a result of a single force, which is mg sine theta. Okay, and so right now I'm going to go ahead and solve for the acceleration of the object. Obviously you can see that we'll be able to cancel out the masses. So the answer to this problem will not depend at all on the mass, right? Only depends on gravity and the angle of the inclined plane. Just to remind you, that angle theta is the same as this angle. So this is 30 degrees also. So the acceleration in this case is equal to g times the sine of theta. And so a is equal to 10, times the sine of 30, and in that case that would be 5 meters per second squared. So the sine of 30 is 0.5, and 0.5 times 10 gives me 5.0 for the acceleration. Okay, so that's the first step. Right, so this older way of doing things is to use the net force acting on it, and then I'll go to my kinematic equations. So the old way of doing it is use either force first, then go to kinematics, or use kinematics first and then finish with forces. So now that I have the acceleration, I can use this equation, v squared equals v naught squared plus 2ad, to come up with the final velocity of this thing. So this would be 2 times 5 times 20 to give me a velocity of that says 14.1. Okay, so not super complicated problem, but it does require 2 steps. I use the net force to get A, then I use A with the kinematic equation to come up with the final velocity. Okay, so here's the difference with the energy approach. In the energy approach, I would only look at sources of energy. And it turns out for this, there is only one source of energy, and that's the height. So this object has some potential energy, and I want to allow it to slide all the way to the bottom of the ramp, at which point it will have 0 height. So it's going to slide down the ramp, and when it gets to the bottom of the ramp, it will have no more height, so all of the potential energy will get transformed into kinetic energy. So I can set up this equation that EP is equal to EK, or that is to say that mgh naught, the initial potential energy, is turned into the final kinetic energy. And just like we saw in the previous equation, the mass will not matter. Does not matter what the mass of the object is. In fact, I've never said what the mass of this object is. And so now I can solve for the missing v by saying that v squared is equal to 2gh naught. And just at this point, let me just point out how similar these equations are, right? Because if you look back at the previous one, like how did I solve this equation? I got v squared equal to 2 times the acceleration, right? So in this case, the acceleration down the ramp times the displacement. In this case, I'm using a different acceleration, so I'm using the vertical acceleration of gravity, and of course, if I'm going to use the vertical acceleration, then I want to use the vertical height. So if you look at how the numbers are going to pan out, it's going to be v squared is equal to 2 times 10 for gravity, and the height was only 10, so this is obviously going to produce the same answer. Okay, 10 times 10 is 100, and 100 times 2 is 200. So over here, 2 times 5 is 10, 10 times 20 is 200. So I get v squared equal to 200, and over here I also get v squared equal to 200. So v is obviously equal to 14.1 meters per second on this side, just like it was on the other one. The only difference is that this only required a single equation. And again, this is all assuming that there is no friction. So it turns out that using the energy approach, that if there is no friction, it doesn't matter what the angle of this slope is. It won't make any difference at all. The energy comes entirely from the potential, and the potential is going to get turned into kinetic at the bottom. And so as a result, all we need to know is how high was the ramp? How high did the object move downward? And I can work out what the final velocity is without having to care whatsoever about what this angle was. The angle could have been 30, 50, 60, 10, wouldn't make any difference. I'm still going to get the same answer no matter what, because the only source of energy is the potential energy that it had to start with. So based on this, let's take a look at a problem that's very common to look at in physics, and that is roller coasters. We're going to see how fast a roller coaster will be moving, and this little trick about not having to worry about the angle, that's going to be super helpful, because this was pretty complicated, coming up with the force diagram and figuring out what part of the force was causing the thing to accelerate. That's a complicated problem. But when you don't have to worry about the angle or any of the forces that are acting on it, all you worry about is the energy. It's so much easier to solve that problem. So let's take a look at a few examples of the roller coaster problem. So let's take a simple example where we have a first hill of a roller coaster is 25 meters high, and the second hill is 17.0 meters high. And each roller coaster car is 250 kilograms. So let's draw what that looks like. So the first hill (25 meters tall), and the second hill only 17 meters tall. So this guy is 25. And this guy is only 17 meters tall. So here's another interesting aspect of this problem. It doesn't matter what the shape of the hill is. So the hill can have bumps or curves. It doesn't make any difference. As long as there's no friction, all that matters in determining how fast is the car going down at the bottom is going to be how high was the hill. That's it. How much energy did the car have at the top? And if you can figure out how much energy the car had at the top, then you can figure out how fast the car will be going at the bottom. So let's start at the beginning. So the first step is, if you've ever been on a roller coaster, you notice that they pull the car to the top. So the car moves forward until it connects with a chain, which then pulls the car to the top. So then there must be some work that is required to pull the car to the top. Just like when we were looking at going down the hill, if we assume that there is no friction, then when we go up the hill, we can look very simply at what is happening to the car, what kind of energies are being done. So in order to determine the minimum work, I would simply say that the work that was done, if there is no friction, then the only work that is done is to change the potential energy. Right? So this is sort of a variation on the work energy theorem, but in fact it's not really the work energy theorem, because this is the definition of potential energy. Potential energy is the energy gained by doing work against gravity. Sorry. The potential energy is the energy gained by doing work against gravity. So this isn't really like a new equation. This was actually how we defined the potential energy. So in this case, the potential energy is just the amount that I gained going from 0 at the bottom to the 25 meter tall first hill. So I would say that W was equal to mgh, right? And I would say minus mgh naught, but the initial was 0. So basically all I need to do is to plug these guys in. This is 250 times 10 times the height, which we said was 25, and that will give me, I'm sorry, I apologize. So I set the potential energy equal to the work. I know that this guy cancels out. When we plug in the numbers, we end up with 250 times gravity times the 25 meter tall hill, and that is 62,500. And those would be in units of joules. So the work done is just the amount of work that was needed to raise the car by 25 meters. That's it. We changed the potential energy. There's no other form of energy at this point. And as a result, all we need to do is calculate the potential energy to figure out the work done by that chain that was pulling you to the top. I did not need to know what the force is. I didn't need to know what the angle of the hill is. I don't need to know how long the hill is. I don't need the displacement. All I need to know is how much did the energy change by. That must have been a result of the work that was done. So now the more likely question that you would be asked is to determine the minimum speed, or the minimum speed at the bottom of the first hill. The reason why I say minimum is obviously to get over the hill. So back here, to go over the hill, you'd have to have some velocity, right? But if we assume that at the top of the first hill they let you go with 0 velocity, which is pretty close to being true, the velocity of the car as it goes over the top is pretty low. That would allow me to calculate the minimum speed at the bottom of the car. So let's go back over here. So for this one, I'm not going to think about work. I'm just going to think about the different forms of energy. So at the top of the first hill, and I'm going to start being, instead of writing things that I know already are 0, I'm just going to cut out anything that's not present. So I'm going to look at what kind of energy was present before the car left the top of the hill and what kind of energy was present at the bottom of the first hill. And those are the only ones that I'm going to write. So I know that at the top of the first hill that it had potential energy. And I know that at the bottom of the hill it won't have any potential energy anymore, but it will have kinetic energy. So in this example, mgh equal to 1/2 mv squared, that's h naught, the initial height. I know that it will not depend on the m's, and I will end up with just this equation that v squared is equal to 2gh naught. I'm going to multiply by 2 to get rid of that 1/2. That'll move it over to the other side, and now we can go ahead and plug those numbers in. 2 times 10 for gravity times the height of 25. And then don't forget you need to square root that. So once I get the 2 times 10 times 25, 2 times 10 times 25, that's 500, and then I need to take the square root of that, and that is 22.4. 22.4 meters per second will be the speed of the car, the minimum speed. Now it could be more because it's probably pretty likely that the car did have a little bit of kinetic energy. I mean, it would be kind of hard for the car to go over the top of the hill without moving at all. So most likely there's a little bit of kinetic energy, but I don't know what it is because at no point was I told what the velocity of the car was as it went over the top of the hill. Maybe I would know. Maybe I would know what the speed is, but in this particular example I wasn't told that, so all I can do is calculate the minimum speed. I know the car will be traveling at least 22.4 meters per second, but probably more likely a little bit faster because of the unaccounted for kinetic energy. So in this one we did not know what the initial speed was going over the top of the first hill, but let's move on to the most complicated version that we're going to look at, and in this case we will know. So let's assume that as the car passed over the first hill that we did know that the speed was 1.5 meters per second. So now I don't want to determine the speed of the car at the bottom of the first hill. I want to know the speed at the top of the second hill. So just to remind you, that's up here at the top of the 17-meter tall hill. So up here at the top of this hill we're going to have kinetic energy because we have 1.5 meters per second speed. We're going to have potential energy because we're 25 meters above the surface, and that energy is going to transform into greater and greater kinetic energy, more and more kinetic energy, until it's all kinetic energy at the bottom here, and then that energy is going to transform. Some of the energy will get transformed back into potential energy, but not all of it. Without friction, not all of the energy will be transformed into potential energy. And when I get to the top of the 17-meter tall hill, I will still be moving with some velocity, and that's what I want to know. I want to know how fast. So I have potential and kinetic, and I'm going to turn that potential and kinetic into potential and kinetic at the top of this hill. And I'm going to use that to solve for the velocity. So in the last problem, I cut out some of the things from the equation, but in this new one, I really won't be able to do that. So EP plus EK must be equal to EP plus EK. So just plugging in all of the formulas, mgh naught plus 1/2 mv squared must be equal to mgh, the final height, plus 1/2 mv squared. So, obviously in this case, we can once again get rid of all the masses, and we can go ahead and start plugging in all the numbers. So in this case, it is 10 for gravity times the initial height, which was 25. As it passed over the top of the 25-meter tall hill, the first hill, it was going 1.5 meters per second, so that's plus 1/2 1.5 squared. That must be equal to 10 times 17, the height of the second hill, plus 1/2 v squared, my final velocity. So I'll go ahead and do each of the numbers separately so that you can sort of see the calculations getting worked through. So first is 10 times 25 is 250, plus 1.5 squared times 0.5. That's 1.125. That must be equal to 170 plus 1/2 v squared. Excuse me. So we'll move all the numbers over to the other side. So 250 plus the 1.125 is equal to 251.125 minus 170. I'm going to subtract the 170 to move it over to the other side, and that is 81.125. That's equal to 1/2 v squared. We'll multiply by 2. That's 162.25. And then all we need to do right now is to take the square root, second function, square root the answer, and we end up with a speed of 12.7. 12.7 meters per second. So again, all we looked at was the energy. We did not pay attention to any of the forces, none of the displacements. Don't care how far the car traveled, only the fact that it went up over a hill and had a certain amount of velocity, and that velocity transformed from combination of kinetic and potential to different combinations of kinetic and potential. But in the end, I knew based on the height what the velocity that it must be when it passed over the top of that second hill. Okay, we're going to finish this problem with one last look at what happened to all this energy. So look, at the beginning of the top of the first hill, I had this energy. So I had some potential and some kinetic energy. And obviously, at some point, we have to get rid of that energy. I mean, otherwise the car is going to go on forever. So we're going to assume that based on example C, that the braking force of the car is 3,000 newtons. And so what we want to figure out is what is the minimum distance needed to bring the car to a stop. So for this one, I'm going to write it this way. I'm going to say that the potential plus the kinetic at the top of the first hill will be equal to the work done by the braking force. So in this case, one thing that's going to be a little bit different, mg h naught plus 1/2 mv naught squared will be equal to the work done by friction. That's going to be F times D. Now, one thing you'll notice is in this particular example is that the m's will not cancel out. Okay, so as soon as I take this thing to work, and I'm not asking for the acceleration. Now, if I was asking for the acceleration, I'd plug in ma for F. But in this case, I actually want, I need to use that force, and that force is not based on the mass. So I cannot cancel out the m's. All right, and what I'm looking for is this guy. I want to figure out the distance. So I can go ahead and start plugging in all the numbers. We had 250 times 10 times 25. That was my mg h naught, plus 1/2 250 times 1.5 squared. And that must be equal to 3,000 times d. So putting the numbers together over here, 250 times 10 times 25 equals 62,500 plus 0.5 times 250 times 1.5 squared. That's 280.25, 281.25, and that must be equal to 3,000 times D. Okay, so putting those two numbers together, plus 62,500, that's 62,781, and then I'm going to divide that by 3,000 to get D. Divided by 3,000, and I get a minimum stopping distance of 20.9. And the reason I wanted to look at this example to finish with is just to point out that very commonly the masses will cancel out, but in this example I cannot cancel the masses out because one of the properties that I'm looking at does not, it's not depending on the mass. I already know the 3,000 newtons, so there's no reason for me to try to break the problem down any further. I could have solved for A and then plugged in m times A and then crossed out the m's, but in this case, and in many cases where, you know, for example, friction is acting on it, well, the friction may not depend directly on the mass, and so in that case the m's do not cancel out. So you got to be careful about canceling out the m's to make sure that every single one of the energies that you're talking about depends directly on m, so that you can go ahead and cross it out. So that's conservation of energy applied to inclined planes, and in the next video we're going to take a look at friction. Friction is a force that takes away from the energy, so it does negative work, and so we'll take a look at how that impacts all these problems if we go ahead and throw in the frictional force.